In this video, we're going to talk about how to set up your test on the Isaac HD test platform. In particular, today we'll talk about setting up a basic pressure decay test. What are some of the things to set? What are some of the pitfalls to watch out for? And maybe how to optimize the test to get the most out of the tester so that we can get the most amount of test parts through the production line to where there's no doubt that we've found all the good and all the bad parts. So the items we'll need today for this test are our Isaac HD tester. We'll need some example parts. If you have parts that are known good and parts that are known bad, that's a great thing. If you have a known specification, we make a device called a leak standard or a transfer standard, that if you're fortunate enough to have handed a spec down to you, that we can make that spec into a physical form. This one happens to be 0.1 cc's at 10 psi, meaning this device will have a leak rate of 0.1 cc's per minute at an inlet pressure of 10 psi. That happens to match up to the application that we're going to be testing. We have a simple catheter device today that we'll set up from the beginning. From Power Up, we'll go to the program menu by hitting the Gears button. In the Gears button, it goes right to the pressure screen. We're going to fill in as much of this information as we have. Some of it we'll kind of guesstimate, and we can go back and forth from the run screen testing it to see what happens. This particular application calls for a 10 psi test pressure. So I'm going to enter in 10 psi as my test pressure selection. The plus and minus tolerance, we typically will recommend you start at 10%. So we'll move +1 and -1. This will allow for a test pressure of 9 to 11 psi. Jumping ahead to the settings, the actual test setup, this is a great place to start. These are our default values for a test setup. We have a 2-second fill, a 2-second settle, and a 3-second test. Depending on the volume of the part will determine how long we actually need to fill. The secondary item we need to think about during the fill is, do I have a soft part or a hard part? If the part is soft, it's going to act like a balloon. As we fill it with pressure and we don't have enough fill time, the part will continue to expand, and when we go into the settle and test step, that expansion will turn into a decay because the volume is increasing, and we will fail the test. So in this particular part, it is a softer part, but it's not soft enough that we have to spend too much time. So we'll start with a 2-second fill. The 2-second settle is the amount of time we allow for any thermodynamics to take place. At 10 psi, there is some amount of compression of the test air that's going to turn into heat, and as that heat then goes back to equilibrium, we'll turn into a pressure drop. Now we're just going to watch for a set amount of time. Use caution that too long of a test time opens you up to outside influences. So we'll go ahead and leave all of our test time parameters, 2, 2, and 3 the same. We'll have a 1-second vent for safety to allow the part to be emptied prior to us removing it. And a decay value, we're going to leave it at the decay of the default, which is 0.05 psi. So in 3 seconds, if we decay more than that value, the test will be considered a failure. One feature that I like to turn on when I'm setting up a test is called Evaluate at End of Test. If the box is unchecked and the value drops below 0.05, it will stop. Even with 2.9 seconds remaining in the test, it will stop the test. When you check this box, if the decay value goes past the 0.05, it will continue on to run the test step for its entirety. But this allows me to now kind of group out parts to different ranges, finding some that leak more or less than each other, but using the same test time parameters. So let's go ahead and go back to the pressure screen. And one thing we need to do is physically set the regulator into place. We've already set it as far as the program. So what I'm going to do is I'm going to plug the test port and use the valve on checkbox to achieve my test pressure. If it wasn't at pressure, I could use the regulator to adjust it till I reach my test pressure. Then uncheck the valve on box, and now my regulator is set, ready to go. So let's go out and run the actual test and see what happens. To get back to the run mode, we're going to press the play button in the lower left-hand corner. I'm going to attach my part to the test port and run the test. We now get a pressure over time graph for a 2-second fill, 2-second settle, and a 3-second test. We get very little decay because of this. You can see our result is 0.0001 psi. Now we can run our next test by introducing our leak spec in physical form. So by adding this and simply running those same time parameters again, we can see the result according to what our spec says. So now we see that our spec of 0.1 cc's yields a decay of 0.0174 psi. Really what we're looking for is the difference between a good part decay and a bad part decay. Is there enough separation between these two numbers? If you recall, the first test was 0.0001. So we have about 170 times difference between those two values. We typically say that a good test should have a separation of 3 times. So a good part and a bad part should be 3 times each other, no matter what the numbers are. So this indicates to us that we have a very easily achievable test that will be very repeatable, and then we can easily find pass and fail results. So if we ran multiple parts with the leak standard and got an average of those decays, we can now come back in and enter the new decay value that will cause a failure. So if the limit that caused the failure, the average, was 0.017, we could leave that value. But there will be some tests where you might get down to 0.0169. Now, is that value a real leak? It's so close to the leak, it's closer to a failing part than it is a passing part. So we will typically say, let's come off of that at least 10%. So if we take 10% of that number, we can now go to 0.016 as a good place to start. So now we're for sure going to catch everything that has this leak. So we can go out and prove that by running a test. We still have our 2-second fill, 2-second settle, and a 3-second test. We get a failure because we have more decay. So running the same part, this being a known good part, easily achievable that it's a good part. This can also be done if you had a device that leaks versus having an actual standard. You could make a device that has the manufacturing defect that you're looking for. Will allow us to do the same thing we've just done with the leak standard. The other thing we can do now to optimize this test, because we have a great difference between a good and a bad part, we can actually start cutting some of these times down. So let's go ahead and just take everything in half. So we have a 1-second fill, a 1-second settle, and a 1.5-second test. We're going to do the same 2 tests again. We're going to take our part, which we believe is to be a known good part, and we're going to run it. And again, we get a very small decay value in those times. We run it now with the leak standard attached to it. We'll get a different decay because we're only looking for a shorter amount of time, but do we still have the 3 times separation? In this case, we do. We have about 80 times the separation from a good and a bad. So what you're going to find is there are many variations of test times. It really depends on the leak rate you're looking for, the cycle time your production rate has been asked you to achieve, and then balancing the factors such as, is my part a soft part, hard part? What is the test pressure? High? Is it low? But in this way, you can develop your test based on your needs. If you have any other questions, you can see more information at zaxisinc.com.
As well as you can email service@zaxisinc.com for support.